Well, thank you. It's a great pleasure to be here. So, yes, I'm a condensed matter physicist, and I'm actually going to talk about hardware. I'm not working, I don't have a great mission to solve the problem of storage for big data. I'm really driven by curiosity and the fundamental physical processes. However, it makes sense to work on problems that have some practical use. Okay, so I do have a laser pointer, but I thought that would happen. It's pretty sure it doesn't work on this screen. It works on there. Okay, so I will do without that. Yeah, so I'm going to address the challenge of storing ever bigger data. And this is what I'm going to talk about. I'm going to give you some facts and figures about the scale of the problem, and so why we need to address it. And then I'll talk a little bit about hard disk drive technology, which is really the workhorse today for storing information in the cloud. The industry that makes hard disk drives talks a lot about scaling, as do the people who make processors. In order to say what we can do about some of the problems we face, I need to explain a bit about how it works. So I'm going to give you a quick introduction to magnetism. Maybe I should ask, I mean, who here has a physics background? Okay, so quite a few. Who has no physics background? All right, okay, so I need to navigate carefully through it. And then I'll introduce you to what's known as the magnetic recording trilemma, which is sort of the showstopper for scaling and why we need to do something else. And I'll tell you about one of the preferred solutions, heat-assisted magnetic recording, something which will actually be manufactured in the UK, because we have one of the world's largest manufacturers of disk drives in the UK, in Northern Ireland, that's Seagate. They produce something like 30% of the world's supply of magnetic recording heads in their factory in Northern Ireland. And they're working on this. Then I'm going to say briefly what I do. I'm interested in making things quicker, so we need to watch things happening on very short time scales in order to do that. So I'll explain a little bit about how we do it. That will lead into what I think is going to replace heat-assisted magnetic recording. That's beyond the scaling roadmap. And I'll also then switch gear and talk a little bit about actually how we read the data back from disk drives. It's rather interesting how we do that. And it also leads to another technology for storing information in the form of round chips, magnetic round chips, which might rival the solid-state memory in your laptop, for example. Okay, if we don't go that far, let's just enjoy how far we get. So let's see how we go. Okay, so what does big data imply for hardware? So here are some facts and figures that I scraped from the internet a couple of days ago. One has to be very careful looking at these websites because they all say different things, but a pattern does emerge if you look at a number of websites. So this is from a site which is worried about storage for business. And they tell us that the United States, and this was in 2016, the United States stores about 3.5 exabytes of data. And exa means times 10 to the 18. Also, that data storage requirements grow at a rate of 40% per year. So actually that should be about 10 exabytes if demand has grown at 40% for the last 3 years. And actually, if you scale that up for 10 years, you get a 30 times increase in the demand for data storage, not 50, but as I said, if you look at different sources, you get different answers. But the overall picture is the same, that there is an exponential growth in the requirement for data storage capacity. And actually, storing data, searching it and retrieving it costs energy as well. And you may have seen statistics of this, or similar statistics before. So this is one I looked at recently. One Google search, when we type something into Google, and Google goes and searches its data farms for the answer, a Google search requires about 1 kilojoule of energy. And that's equivalent to running a 60-watt light bulb for 60 seconds. And Google carries out more than 1 trillion searches a year. So that's going to be quite a lot of energy. And yet another source estimates that our information technology will consume 20% of the world's energy supply by the year 2025. So that 20%, it might be 15, it might be 25%, but it is becoming a significant number. So, as you know already, big data, it's a movement. We're finding ever more things to do with data. We're getting bigger data sets that we want to search, and that number's only going to go up. And so that places a real demand on the hardware that we use in information technology. I'm not going to speak to all of information technology. I'm just going to focus on data storage because that's what's relevant to what I do. So what it means for that technology is, firstly, it needs to be smaller. So each little bit of information that we store has to occupy a smaller volume so that we can store more of it in a feasible way. Our technology needs to be faster. We've got bigger data sets. We don't want to wait 50 times as long to find the answer. We want that answer in real time most of the time. And clearly, it also has to be more energy efficient if it's to be feasible. So that's the problem, I guess. So we need smaller, faster, and more energy efficient. And as you know, a lot of our data is now stored in the cloud within data farms. And what they contain are essentially lots and lots of hard disk drives. So you see great big racks of them, and there's some redundancy in case one fails, another one kicks in, so you don't notice. And they contain disk drives because you've got rapid access to different parts of the disk, and it's actually the cheapest way of doing it. And that technology has evolved according to a Moore's law. So this is a law that says the capacity is going to double every 18 months, something like that. And the industry is very fond of these historical plots, where on the vertical axis you've got the areal density, the number of gigabits stored per square inch on the surface of the disk drive, and that's plotted against the year of production. So this is quite an old one, it only goes up to 2020. And the point is, it's sort of roughly linear, but as the technology changes, the gradient can change a bit. So we've got two curves here. These are the hard disks in red, and these are flash products for comparison. So you can see that the hard disk drives are always ahead of flash in terms of the areal density. Okay, so how does a disk drive actually work? You probably know in general terms already. I did have a demonstration that I was keen to bring, and then I wasn't really sure it was going to work in front of an audience of this size. You all have to come up and stand over it. And then Miranda said, make a video of it, and I had good intentions, but it didn't quite happen. So I'll tell you instead. So, okay, the information is stored on the disk. In fact, you have multi-platter systems. There may be 3, 5 separate disks. So the information is stored in a track like this, and the red or yellow represents a 1 or a 0, so everything's stored in binary format. The coating is magnetic, so you can think of each of those regions just as a little bar magnet. So we all know magnets are red on one end and blue on the other end, right? So what this means is either the red end is pointing up or the blue end is pointing up. That's how we represent 1 or 0. And to read and write the data, we have transducers on the end of what's known as the slider arm. And the right transducer is essentially an electromagnet. So it's some piece of ferrous material with a coil wrapped around it. We put current pulses through that, produces a magnetic field, and magnetizes the surface of the disk. What's surprising about it is the scale of that device. So it needs to write in a region less than 100 nanometers in width. So you need to make a very, very small electromagnet. And that's a very difficult engineering task, but clearly it can be done. And then you have a series of different tracks, concentric tracks, and then your areal density is the linear density multiplied by the density of the tracks in the radial direction. And so on the bottom of the slider arm, there's something here that looks vaguely like an electromagnet with some windings, but not from where you're sitting. I can see that. There's also a sensor, which I'll come back to later to read the data back. So that's basically what a disk drive is. Okay, so I want to tell you a few things about magnetism. And magnetism's a very old subject. We've known about it for an awfully long time. So the Chinese knew about it. In fact, they used it in compasses. The Greek writer Thales, he talked about the lodestone. This is magnetite and iron oxide, and how it could be used to attract things. And then it's relatively recently that we understood more. So in the 16th century, Gilbert figured out that the Earth is actually a great big bar magnet. So that's why compasses work. But we didn't really make a lot of use of it until the Victorian era, and then Michael Faraday and others developed electric motors and dynamos. And then really only 50 or 60 years ago did we start using magnets for recording information. And the first ferrite core magnetic memory was invented in 1947. But today, magnetic materials are everywhere in our modern environment, and the technology that we use. They're used in sensors and actuators, in all sorts of machinery, motors and so on. Interestingly, they were used in communication devices since the Second World War. They were very important in radar technology. In short, magnetic materials violate time reversal symmetry, and that means that waves propagate backwards and forwards through them in a different way, and that's known as non-reciprocity, and that's actually very important in microwave technology. And then finally, of course, they're used to store information in different formats, in disk, tapes. People never see tapes these days. I mean, older people like myself used to have a tape player in my car. They're still used for backup, but you're probably not aware of them. And then we've got RAM chips as well, which can be magnetic, which I'll talk about later. However, interestingly, there aren't all that many different magnetic materials available to us. If we look at the periodic table, the ferromagnetic materials are just cobalt, iron and nickel. They're next to each other in the periodic table. And actually some of the rare earth materials are ferromagnetic as well, but just not at room temperature. So gadolinium is the best of them, and it loses its magnetism just below room temperature. Okay, so we might wonder where that magnetism comes from. And our everyday experience is that if we take a wire and just attach it to a battery, it generates a magnetic field. So this gives us an idea. Let's look inside the material. Let's look at an atom. It's got electrons in it. We can think of them as being in circular orbits. So that's like a current in a wire. So that should generate a magnetic field. Or we can say that it has a magnetic moment associated with it. And actually, so it does. But actually, that's not the main cause of the magnetism that we see in iron, cobalt and nickel. It has a different origin, and it's in fact associated with an intrinsic property of electrons. So this property is known as spin. And spin you can think of as the electron spinning about an axis through its centre. So this is complete fiction, because the electron's a point-like particle, so that's rather meaningless. But it's just something that comes out of relativistic quantum mechanics. And importantly, there is a magnetic moment associated with this spinning of the electron. And it turns out that this spin can point either up or down. A magnetic moment that's up or down. And this was actually confirmed in the 1920s by Stern and Gerlach. And what they did was they just took a beam of electrons and they passed it through a magnetic field. That's what the B means. In fact, it was a rather non-uniform magnetic field. That's an important detail. And the beam split into two. And that was the verification that the electron had this property spins. So each electron's got a magnetic moment. Each electron is actually a bar magnet in itself. Okay, so the reason that iron, cobalt and nickel have this magnetic property is due to the spins associated with the electrons in the material, and furthermore, all of those little bar magnets associated with electrons have to line up and point in the same direction. And there's another magical interaction that takes place. It's known as the exchange interaction. It's a quantum mechanical thing, and it has to do with the interaction of the charge of different electrons. So it's a rather subtle thing, but it works. That's all we care about. And that makes those elements ferromagnetic. Okay, so I just want to tell you a couple more things about magnetism. So if we think magnets, we think, yeah, okay, my fridge. I've got a fridge magnet on my fridge door. So I know that that fridge magnet, that's a magnet because it sticks to the fridge. Fortunately, my fridge door doesn't stick to my oven. That would be a problem. Okay, but the fridge magnet sticks to the fridge door. So in a sense, the fridge door is also magnetic, right? And it's made of steel, which is mainly iron. So of course it's going to be magnetic. So what's the difference between the fridge magnet and the fridge door? So the fridge magnet would attract the oven, but the fridge door wouldn't. So the difference in some way. And then we have to look inside those magnetic materials. So this is a bar magnet. And it looks like planet Earth. It's got a similar magnetic field that it generates. And in fact, that magnetic field is a store of energy. So that's actually a high energy state. It would be energetically favourable for that bar magnet to split up into 4 bar magnets with this pattern. And in fact, that configuration generates absolutely no stray field. So that's a lower energy state. That's the fridge magnet, that's the fridge door. So how do we actually get one or another? So actually there's a little dividing region between these. It's called the domain wall, but we don't need to worry about that too much. So the reason that they're different is a fridge magnet is actually fabricated and prepared so that it's in this state. And basically what you do is you inhibit the formation of this pattern. So this isn't allowed to happen. So this is actually a metastable state. If you heat it up, actually it will turn into that. Okay, so that's how they're different. And these 4 regions in here are what we refer to as magnetic domains. Okay, so things can be magnetic even if they don't attract other things. All right, so let's go back to disk drives. I'd like to explain where we are with disk drive technology. So this looks like the track that I had on the schematic of the hard disk drive previously. So indeed, these are written bits of information. That image was taken with a magnetic force microscope. And there are some little other things on the side. No, these are for tracking. These are just to guide the recording head so it stays on the data rather than drifting off somewhere else. That's why they're there. But if we look inside one of these, so if you can think of each of these as being a sort of little domain in itself. If we zoom in further, then we find that each of those bars here is actually composed of many grains of material. And if we look at the boundary between, say, this and this, we zoom in, because it's a granular material, in fact that dividing region is rather jagged when we look at it with sufficient magnification. So one of our bits of data contains many grains. There's a jagged edge, and that jagged edge gives rise to something rather boring called transition noise in recording. And it's a limit on the signal-to-noise ratio in the disk system. And that's a problem. So the people who make disk drives are always fighting against transition noise. And the way to reduce transition noise is actually to make the grains ever smaller. If you make the grains smaller, you can smooth out that transition again. So that's what they want to do typically. But there's a problem. You pay a price for making smaller grains. So these grains are now the order of 5 nanometers in size. That's very, very small. And the magnetic moment of the grain, which is represented by the arrow, that's the way it's magnetized. In something that small, it's a little bit of, like a bit of pollen in air. It's buffeted by its surroundings. There's thermal noise. So in fact, this arrow is sort of jiggling around. And if you make it smaller, it gets worse. The environment can perturb it more, so it becomes thermally unstable. So you'd like to make the grain smaller, but you can't because they'll become unstable. So what they do in the recording industry, they actually make a virtue of this. So they use what is known as thermally assisted reversal. So let me explain this diagram. So this is our particle, and this arrow tells us the direction in which it's magnetized. And this is a magnetic field, which is trying to align it. So this would ideally like to be parallel to this. So let's switch off the field for a moment. The grains are designed so that they've got two stable configurations. Either the arrow points to the left or it points to the right. And that's a little bit like a marble stuck on a, I don't know, a skate park, or a skater stuck on a skate park, you know, and these are two valleys. And these are the points of minimum energy, right? You fall down to the bottom of the valley. So if you're in there, pointing to the left, how do you get to the right? Well, maybe you're a bit hot and bothered, so you're sort of jiggling around in the bottom, but you still have to get over this barrier. So there's an energy barrier between the two stable states. So what you do is you apply that magnetic field, and that has the effect of reducing the height of the barrier. Okay, so we've made it smaller now compared to there. And because this is jiggling around due to thermal excitation, if we make it low enough, it will jiggle around and go over to the other minimum. Okay, and then we switch the magnetization. And that's essentially what we do when we write data on a disk drive. So that's the scenario for just one of these grains. That's what's happening. Okay, so the problem is the famous magnetic recording trilemma. So we'd like to increase storage capacity. So we could do that by making the grains smaller. But if we do that, they may become thermally unstable. So what can we do about that? Well, if we go back, actually, what we need to do is we need to engineer a better material that's got a higher barrier, right? Because then it can't just get over the barrier any old how. It should be more stable. But then there's a problem with that, which is that to pull the barrier down again, you need to apply a larger magnetic field. And the problem now is that the magnetic field that you can generate with the transducer in a disk drive is limited by the choice of materials that nature gives you. Nature gave us iron, cobalt and nickel. They've got a certain magnetization strength, and we're already using all of it in the right transducers that we've got. Okay, so if you make the barrier higher to make it thermally stable, you need a bigger magnetic field, and that makes it less writable. So the trilemma is that you can pick two of those three properties, but you can't have them all at once. And really this is the limit on the type of recording that I've just described. And we've already reached that point, so we're in trouble. So the disk drive industry is, they're engineering sort of workarounds. So what they're doing actually is they're making the tracks closer together. So that's an easy thing to do, but there's a limit to how far you can push that. So after that, you need new paradigms for the recording process itself. And here are some ideas. So this is what I've just described. This is the conventional process. But what about doing this instead? When we come to apply the magnetic field, how about if we heat it first? If we heat it, then actually that decreases the height of the barrier. So you can see this barrier squashed it down by heating. That's what's meant by heat-assisted magnetic recording. The other thing that you can do is somehow excite it in the potential well that you're trying to get out of. Okay? And the way to do that, actually, with a magnetic system is to apply microwaves to it. If you drive a magnetic material the right microwave frequency, magnets do a rather interesting thing. They start to precess, like spinning tops. Okay? So the direction of the magnetization will sweep out a cone like that. And if you keep on pumping it, the cone opens up, it keeps going, and then it will fall down into the opposite state. So you're probably wondering, well, that sounds great, but how are we going to do that in a disk drive? And of course that's the challenge. And in fact there were working prototypes of both of those paradigms. So it can be done. The problem is making it reliable and getting the performance characteristics out that you want. Okay, so this, I hope, is going to work. So this is one I stole from Seagate. It goes a bit quick, so this is a visualization of how heat-assisted magnetic recording works. So it's played already, so what I'm going to do, I think, is try and play it again and then just stop it at key points. So what we have here is, this is the surface of the disk, and this is the read-write transducer on the end of the slider arm in a disk drive. And if I move it forward a little bit, just pause, oops, not far enough. Okay, so now what's going on here? So what we've got here is light from a semiconductor laser, and it is being pumped down to the recording head. And you probably think, well, how do you do that? How do you get light down there? Well, what you've got is actually a planar fibre optic. So you know, light can be passed through, confined and passed through fibre optics. Well, a fibre optic doesn't need to be a cylindrical cross-section. You can make a slab. In fact, it's easier to make a slab, and then you can pass light through that. So there's a slab which is guiding the light down here, and then at the end there is a little disc of gold. So it's a circular disc, but it's got a little peg on the end. And that's very carefully designed so that it generates an optical resonance at the bottom. And the key feature of this is that that peg is considerably smaller than the wavelength of the light that's coming into it. As you may know, that if you take a microscope and try and focus light down with a lens, you can only focus the light to a diameter of about half a wavelength. So this is a near-infrared laser. It's probably 800 nanometers wavelength. So you get a 400 nanometer spot. And that's rubbish from the point of view of magnetic recording, because our bits are already much less than 100 nanometers in size. So we need to focus the light down to substantially smaller diameter than that. And therefore we need a trick. And the trick is to use this peg, which supports what's known as a plasmonic resonance. So what's happening is the light comes in, it excites the electrons in the gold, and they all sort of jiggle around at the frequency of the light, and they create a very strong electromagnetic field right there. And what that does is it heats a very localized region of the magnetic material beneath it. So what we're doing is we're softening up that bit of magnetic material, and then this is the electromagnet. You can see there's some bits of ferrous material with a coil wrapped around it, just as I promised, and that's going to generate this magnetic field, which loops out here, and then this interacts with the recording medium, which has just been softened up for the purpose of doing that. And then actually the trick is to get the heat out again, so it doesn't become unstable. So these recording media are now carefully designed with heat dissipation in mind as well. So actually, building a successful recording drive is a multifaceted problem. There are all sorts of physics that go into it. It's not just about magnetism. It's about thermal modelling. It's also about tribology, because the flying height of the recording transducer above the surface of the storage medium is only a couple of nanometers. So, you know, if you think it's spinning round at 100 RPM or more than that, to be only a few nanometers from the surface of the disk, how does that work? How could that possibly work? And it turns out that there's an air-bearing surface. You just can't get the air out of the way quick enough for the head to crash into the disk. That's essentially how it's done. There are also special coatings put on, it's probably a carbon coating or something like that, it's on the surface of the disk as well to help. Okay, so that's what heat-assisted magnetic recording looks like if you look in sufficient detail. Not too far. Okay, so armed with this energy-assisted magnetic recording, we can revisit the areal density map against year. And this is where heat-assisted magnetic recording starts, around 2020. In fact, I've already seen these drives. Seagate take them to conferences now, and you can look in the side and you can see sort of the flashing lights, which apparently are the laser diodes from the disk drives doing their stuff. And those are aimed at the server market. And the problem they've had with those disk drives is actually the reliability of the little gold disk. It turns out that if you get it hot enough for long enough, it deforms. So, but apparently for the server market that doesn't matter. Everything's got a finite lifetime, obsolescence is built in, and as long as you can make it work for a certain length of time, that's okay. Okay, so that's going to take us to 2023 apparently. Then things will change a bit again. The idea is to move to recording media where the surface of the disc is already patterned into discrete dots, and I guess each one is a single grain of material. So that's just increasing the fidelity of the film in which the information is stored. But the question I'm really interested in is, well, what happens after that? Okay, so I want to tell you quickly about a very surprising experiment that was done in 1996, which coincidentally is about the time I started doing what I'm currently doing, and this was very inspiring to me at the time. So it was a very simple experiment. Well, in one way it was simple. So a couple of people in France, in Strasbourg, took a film of metallic nickel and they fired a laser pulse at it. It was a very short laser pulse, 100 femtoseconds, which is 10 to the minus 13 seconds in duration. So that sounds incredible that you can do that, but actually ultra-fast laser technology is a pretty common thing now. You know, everybody's got one. We've got several of these in our lab. And so what they did was they fired it at the film, and then they used another pulse to see if the magnetization of the material had changed. And what they saw was that the magnetization decreased very suddenly after the arrival of that first pulse. In fact, it decreased by a factor of about a half in a time less than a picosecond, less than 10 to the minus 12 seconds. So, I mean, why is that surprising? Well, it's surprising because at the time people thought what you would do is you just heat up the metal, heat the electrons in it, and the spin of electrons, that lives in its own little world. It's actually quite well detached and decoupled from the rest of the film. So people thought that that would take a nanosecond to decrease to that sort of level. So a nanosecond is about how long it takes to write a bit of data on a disk drive at the moment. So if we want to go much faster than our present recording rates, we need to be very interested in processes like this, where we can change the magnetic state on much shorter timescales. And this provided the insight and encouragement that this could be possible. So, okay, to digress slightly, I'm going to ask, well, why does small and fast matter? So here's something that's small and fast, it's a hummingbird. And actually, hummingbirds are quite a challenge to visualize and to photograph because they flap their wings very fast. So why does it matter? Well, firstly, because we're curious. There are lots of examples, even of biological organisms where things happen quickly, and for a long time we just didn't understand how they did it because of our own visual faculties not being able to keep up. It's also interesting to us because small and fast things underpin how everything works in the natural world and in our environment. So, for example, an atom within your body, it vibrates at a characteristic frequency, and that frequency is about 10 terahertz. So that means that it oscillates about 10 to the 13 times per second. So happens very, very quickly. And if you want to change it or control it, then you first need to see it happen on those timescales. Alternatively, in our electronic technology, when we apply an electric field to something so that we generate a current, we know that electrons move, but they also scatter. That's why we have finite resistance rather than everything being superconducting. And the time taken for an electron to scatter, we accelerate it, then it scatters. That time is about 10 to the minus 14 seconds. So again, it's an incredibly short time. So again, if we want to control and modify electronic properties, we need to be able to see things happening on those sorts of timescales. And if we can do that, then of course we can create more powerful technology, and we know that our computers already have gigahertz clock speeds. And as I said, a bit of data is stored in a time of about 1 nanosecond. So we need to go to shorter time scales if we're to do better. Also, data transmission rates exceed this. We've got many gigabits per second. So I'm just going to skip over this. I quite like talking about the human eye. It's rather interesting because it gives you all sorts of inspiration for building different optical devices. But I'm just going to point out that the timescales that the human eye can sense are limited to things that happen on timescales of greater than the order of 100 milliseconds. And we know that because when we watch TV, the frame rate is either 50 or 60 hertz. And for us, it looks like continuous motion. But in fact, it's just a series of photographs strung together, played back to us sufficiently quickly that we don't notice. This is sort of a quite interesting football digression we could have, but we won't do that tonight. No? Okay, so how do we study these small systems in motion? So there's the disk drive. We'd like to see what's going on. There's a video camera. Is it going to work? Well, what are the problems? So I've already told you that it takes about a nanosecond to store a bit of data. So if you're going to see that, you need a camera with an incredibly high frame rate. And so we just said, frame rate for a video camera, that's 50 or 60 hertz. It's not 10 gigahertz. The other problem is that if we did manage to take a photograph with an exposure time of less than a nanosecond, then if we illuminate the subject